In the third part of the acid-base equilibrium chapter, we will consider the pH calculations of weak acid or weak base and the predominance domain of the weak acid and its conjugate base. The most important question in the pH calculation of the acid and base is to know when can we neglect the autoionization of water. In case of strong acid, the concentration of HCO+ released in the solution depends only on the initial concentration of this acid. And we proved previously, when the concentration of the strong acid is greater or equal to 3.2 10⁻⁷ molar, we can neglect the autoionization of water. In case of the weak acid, the dissociation is partial, so the concentration of HCO+ in the solution depends on the initial concentration of this weak acid and on its strength that can be known from the value of Ka. So the question now, when can we neglect the autoionization of water in case of weak acid? As we said, the concentration of HCO+ is affected by two factors, the concentration of the weak acid and its strength. As HCO+ released in the solution is close to the HCO+ released from water, in this case we could not neglect the autoionization of water. In this table, we have three cases. For example, in the first, the acid HA is very diluted, so of very low concentration, and suppose the acid is of high strength, so of high Ka. Although a moderate proportion of the acid dissociates, the initial concentration of the acid is so low that very little acid is there to dissociate, gives HCO+ in the solution is close to HCO+ from water. So in this case, we could not neglect the autoionization of water. In the second case, we suppose that the acid is not diluted, so of moderate Ca, and the acid is of weak strength, so of low value of Ka. Also in this case, the HCO+ released in the solution is close to HCO+ from water, and the autoionization could not be neglected. If the acid is diluted, so of low value Ca, and this acid is of weak strength, so of low Ka, the concentration of HCO+ released from the dissociation of the weak acid is close to HCO+ from water, and although the autoionization of water could not be neglected. So in general, and this is the most common case, and this is the general case of our study, for moderate concentration of the weak acid HA, and this acid is of moderate strength, the autoionization of water is neglected. In the pH calculation of weak acid HA of concentration C, and pKa of the couple is between 0 and 14, To calculate the pH, we followed the same steps studied previously. First, what are the species present? Since the acid HA is weak, so it dissociates partially to A- and HCO+, and we have HA remained. The presence of HCO+ indicates the presence of OH-, so OH- has one source, which is the autoionization of water. HCO+ has two sources, the autoionization of water and the dissociation of HA. The reactions taking place are the autoionization of water and the dissociation of the weak acid HA to HCO+ and A-. So the equilibrium constant expressions are Kw and Ka. The principle of conservation of species, A- formed plus HA remained is equal to HA initial, which is equal to C. And the principle of electroneutrality, the quantity of charge negative is equal to that of positive, so A- formed in solution plus OH- in the solution is equal to HCO+ in the solution. As we said in our study in this course, we suppose that the autoionization of water is negligible, so we neglect the concentration of OH- released from this autoionization. So in the expression of the electroneutrality, A- plus OH- equal HCO+, we can neglect OH- with respect to A-, and in this case, the concentration of A- formed in the solution is equal to the concentration of HCO+ total in the solution. We did an approximation in the expression of the electroneutrality. So OH- is negligible with respect to A-, and we obtained A- in the solution is equal to HCO+ in the solution. So what would happen to the relation of the conservation of species where A- in the solution plus HA remained in the solution equal the initial concentration C? We have three cases. The first is A- negligible with respect to HA. That means the dissociation of HA to A- is very weak, and HA is predominant on A-, so HA is weak acid of weak strength. In the second case, the concentration of A- is greater than that of HA, so HA dissociates practically to A-, and A- is predominant on HA. So the acid HA is weak acid of strong strength. And in the third case, we suppose that A- and HA coexist, so we don't have a predominance, and in this case, the HA is weak acid of medium strength. The question now is how to know the acid is weak and how to know the strength of the acid. The acid is weak if it has a pKa value between 0 and 14. And how to know the strength of the acid? The strength of the acid is known from the value of Ka. And in the introduction, we studied that Ka is directly related to the degree of conversion alpha. So the strength of the acid can be known from the value of the dissociation or the degree of conversion of the weak acid. So as a function of the percent alpha, if the dissociation of the weak acid has a value less than 20% or between 20% and 80% or between 80% and 99%. If alpha is less than 20%, the acid is weak and of weak strength. If the value of the degree of conversion of HA to A- and HCO+ is between 20 and 80%, equal to 20% and equal to 80%, so the acid is weak of medium strength. And if the value of the percent alpha is between 80% and 99%, the acid is weak of strong strength. And if alpha is greater than 99%, we know that the acid is strong. To remember that a weak acid would not become a strong acid and vice versa, but a weak acid can behave as a strong acid. Case 1. Calculation of the pH of weak acid of weak strength or the concentration A- is negligible with respect to HA. We write the steps, species, reaction, relations, conservation of species, and electroneutrality as previous. Ka is equal the concentration of HCO+ times A- divided by HA, all are at equilibrium. So Ka equal HCO+ times A- and HA according to the relation of conservation of species equal C minus concentration of A-. So Ka equal HCO+ concentration, A- concentration divided by C minus A-. In this case, case 1, we suppose that A- in solution is negligible with respect to HA remained in solution. So A- is negligible with respect to the initial concentration. And in this case, we can cancel A-, so Ka equal HCO+ square divided by C. Therefore, HCO+ square equal Ka times C. So HCO+ concentration in the solution equal radical KaC. Log HCO+ equal half log Ka plus half log C. So minus log HCO+ equal minus half log Ka minus half log C. Therefore, pH equal half pKa minus half log C, and pH equal half pKa plus Pc. This is the relation obtained of pH when we suppose that the acid is weak and of weak strength. In this relation, we have three terms. We have the pH, the pKa, and the concentration. And since pKa of the couple is constant, so the variables are pH and the concentration, and this relation is valid for interval of pH and for interval of concentration C. So what are the validity conditions for this reaction. As we said, we suppose that A minus is negligible with respect to HA. So A minus is less or equal HA in solution divided by 10. The expression of Ka equal concentration HCO plus times A minus at equilibrium divided by HA at equilibrium. So A minus equal Ka HA divided by HCO plus. And A minus is supposed less than HA concentration divided by 10. So we obtain this expression Ka concentration HA divided by HCO plus is less or equal concentration HA divided by 10. We cancel by HA, so Ka divided by concentration of HCO plus is less or equal 1 over 10. That means HCO plus concentration is greater or equal 10 Ka, implies if you do the log HCO plus log 10 and log K, you obtain pH is less or equal than pKa minus 1. So this relation is valid for a value of pH less than pKa minus 1. In other words, if you calculate the pH of a weak acid by using this relation, and you did not find that pH is less or equal than pKa minus 1, so this relation used is not valid. So our proposal is not valid. So if pH less than pKa minus 1 or equal pKa minus 1, the formula pH equal half pKa plus Pc is valid, and our proposal that the acid we used is weak acid of weak strength is also valid. Now, what is the interval of concentration for this relation to be valid? pH is less or equal pKa minus 1. That means half pKa minus half log C is less or equal pKa minus 1. So pKa plus log C is greater or equal to, or minus log C is less or equal pKa minus 2, or in other words, the concentration should be greater or equal 100 Ka. So if the acid HA you want to calculate the pH has a concentration C greater or equal 100 Ka, so this formula is valid and the proposal is also valid. As a conclusion, for a weak acid HA of concentration C and value pKa of couple, if the concentration of this acid is greater or equal 100 times Ka, or if minus log C is less or equal pKa minus 2, you can use this formula half pKa plus Pc to calculate the pH of this weak acid. In the second case, we want to calculate the pH of weak acid HA of strong strength. In other words, the concentration of A minus is greater than HA, or HA is negligible with A minus. Don't forget, in this case, HA dissociates practically to A minus and HCO plus. So the concentration of HA remained in the solution is negligible, and the concentration of A minus formed is equal to the concentration of HCO plus formed, and these concentrations are of considered values. By writing the expression of conservation of species, the concentration of A minus in the solution plus the concentration of HA remained in the solution is equal to the initial concentration C. In case 2, we suppose that HA is negligible with respect to A minus, so we can neglect HA with respect to A minus, and in this case, we obtained A minus equals C equal HCO plus. The pH formula is equal to minus log HCO plus in the solution, so equal minus log C implies the pH is equal to PC. So for a weak acid of strong strength, the pH formula is directly applied equal PC. This relation is valid for interval of pH and interval of concentration. So what are the validity conditions for this relation? In this formula, we suppose that HA is negligible with respect to A minus, so HA is less or equal A minus divided by 10. The expression of the equilibrium constant can be applied independent of the exercise because it's a constant value equal HCO plus in the solution times A minus in solution divided by HA. So HA equal HCO plus times A minus divided by Ka. And we supposed from the beginning that HA is less than A minus divided by 10. So HCO plus times A minus divided by K is less or equal A minus divided by K by 10. We cancel A minus, so HCO plus is less or equal Ka divided by 10, or in other words, the pH is greater or equal pKa plus 1. So if you apply this formula for the pH of weak acid and you find the pH value obtained is greater or equal pKa of the couple plus 1, so this formula is valid. Now what is the validity condition for the concentration? As we saw, pH equal minus log C. We put pH, we replace pH by minus log C, so minus log C is greater or equal pKa plus 1, or in other words, the concentration C is less or equal Ka divided by 10. In other words, if you have a weak acid where its concentration in the exercise is less or equal Ka divided by 10 or minus log C greater or equal pKa plus 1, you can apply directly the formula pH equal Pc. In case number 3, we will calculate the pH of weak acid by supposing that it's of medium strength. So A minus could not be neglected with respect to HA and vice versa, so A minus and HA coexist. Writing the expression of conservation of species, the concentration of A minus in solution plus HA remained in solution equals C, and the principle of electron neutrality A minus equal HCO plus concentration. To remember that we neglect the autoionization of water, so we neglect OH minus with respect to A minus. The expression of Ka equal the concentrations at equilibrium of HCO plus times A minus divided by HA, and HCO plus equal A minus, so equal HCO plus square, divided by HA, which is equal to C minus HCO plus. So Ka times C minus Ka HCO plus concentration equal to HCO plus square, and we obtained this quadratic equation HCO plus square plus Ka HCO plus concentration minus KaC equal 0. So to calculate the pH of weak acid of medium strength, we have to solve this second degree equation to calculate the concentration of HCO plus in solution acceptable by this relation, then to apply pH equal minus log HCO plus in solution. So as a conclusion, we have three cases and we have three domains of concentrations. If minus log C of the weak acid is less than pKa minus 2, or in other words, if the concentration of weak acid is greater 100 times Ka, so we apply directly the formula pH of weak acid equal half pKa minus half log C, or pH equal half pKa plus Pc. If minus log C is greater than pKa plus 1, or if the concentration C is less than Ka divided by 10, so the weak acid behaves as strong, and we apply the relation pH equal minus log C. In the third case, if minus log C is between pKa minus 2 and pKa plus 1, or if the concentration C is between Ka over 10 and 100 Ka, we have to solve this quadratic equation to find the concentration of HCO plus in solution, then to find the pH. For pH calculation of weak base, we follow the same strategy. B in water dissociates to BH plus and OH minus. As in the case of the weak acid, in the weak base we have also three cases to be studied. First, case 1, if BH plus is negligible with respect to B, that means B did not dissociate to BH plus greatly, so B is weak base of weak strength. In case 2, if BH plus is greater than B, or B is negligible with respect to BH plus, so B dissociates practically to BH plus and OH minus, so B is a weak base of strong strength. And in the third case, where BH plus and B coexist, so B is weak base of medium strength. The strength of the base can be deduced from the degree of conversion alpha of this dissociation, the degree of dissociation or the degree of conversion of the base B. If the percent alpha is less than 20%, the base is weak of weak strength. Between 20 and 80%, the base is weak of medium strengths between 80 and 99%, the base is weak of strong strengths, and if the percent alpha is greater than 99%, so the base is strong. By the same way, never a weak base become a strong base and vice versa, but a weak base can behave as strong. By the same analogy, to calculate the pH of weak base in the three cases, we follow the same strategy as the calculation of the weak acid by replacing the pH by pOH and the value of K by the value of Kb. So we obtain this domains of minus log C and C. If minus log C is less than pKb minus 2, or if the concentration C is greater 100 times Kb, the pOH of the solution equal half pKb minus half log C, and pOH plus pH equal pKw, so we can deduce the pH. If minus log C is greater than pKb plus 1, or in other words, if C is less than Kb over 10, so the base weak behave as strong and pOH equal minus log C. And if minus log C is in the domain pKb minus 2, pKb plus 1, or if the concentration C is between Kb over 10 and 100 Kb, we have to solve this quadratic equation OH minus square plus KBOH minus KBC equals 0, and we have to find the acceptable value of the concentration of OH minus by this equation, then to apply pOH equal minus log OH minus in solution, then to deduce the pH.